Okay, good morning. Today we're going to find out the joint equation of a pair of tangents drawn from a point to a circle. So what is it that we need? We need to find the pair of equations of straight lines. Basically, we need to find the joint equation of a pair of lines which are tangent to the circle when tangents are drawn from this point. Now, if there is a point P outside the circle, there are going to be two tangents, right? And the problem that is given to me is to find the joint equation of both these lines, both these tangents to the circle, so that if eventually they can be factorizable, then I do not have to waste my time trying to calculate the equations of these tangents separately. Okay? So let us suppose it is given the circle x square plus y square is equal to r square and a point P x1 comma y1 lying outside the circle. Okay, and I wish to find out the joint equation of the pair of tangents drawn from this point to this circle. Now, in order to be able to solve this problem, let's do one thing. Let's draw the chord of contact AB. Okay, let's join A and B, and let us consider a point. Let's say there is a point Q, H, comma K on this tangent anywhere. Alright, so it can be a point Q on this tangent. This Q can also be somewhere over here. Now, this is the point whose locus I wish to find. Alright, so if you remember what locus is the equation of a moving point, or rather it is the path followed by a point which is moving according to a given condition. So let's say this Q is moving on these two tangents, and I wish to find out the equation of this, joint equation of these two lines. In that case, what I'm going to do is I'm going to draw a perpendicular from this Q to this line AB, and let's say it meets AB at N. Okay. So I will now have a right angle triangle AQN. Let us also draw a perpendicular from this point P to AB, so that I have another right angle triangle APM. Okay. Now these two right angle triangles are similar to each other. So triangle AQN is going to be similar to triangle APM. I do not think there is any need to explain why these two triangles are going to be similar. It can be seen very easily that this line QN is going to be parallel to PM, which is why this angle is going to be equal to this angle, and the 90 degrees is already equal to each other. The third angle is common. So according to the AAA angles rule, the two triangles are going to be similar. After this, I'm going to say therefore AQ over AP is equal to QN over PM. Can I say this? That because of the similarity, I can say that the ratio of the lengths of the sides of the triangles are equal. That is, AQ by AP is equal to QN by PM. Now, what is AQ? If you ask me what is AQ, I would say it is the length of the tangent. It is the length of the tangent drawn from Q to the circle. Okay? AQ, if you calculate, is going to be the length of tangent. Now, what is the length of tangent drawn from a point to a circle? It is equal to under root S1. Under root of S1, that is, when you put the point Q, or whichever point where you from where you are drawing the tangent to the circle, you put that point Q into the equation of the circle to form a constant value, and that in this case is going to be equal to under root of H square plus K square minus R square. This is going to be AQ. Similarly, AP, what is AP? Is the length of the tangent drawn from P to the circle. That is going to be under root of x1 square plus y1 square minus R square. This is equal to AP. What about QN? QN is equal to the perpendicular distance drawn from this point Q onto this line AB. Okay. In the meantime, what the equation of AB is. If you recall, AB is the chord of contact of the tangents drawn from the point P to the circle. Okay. So what is the equation of AB going to be? It is going to be x x1 plus y y1 is equal to r square. There will be x x1 plus y y1 equal to r square. This is the equation of the chord of contact AB. So Qn, which is the perpendicular distance from this point Q onto this line, will be equal to h x1 plus k y1 minus r square. Right? How do you find out the length of the perpendicular drawn from a point to a line? You put that point into the equation of the line, that is h comma k will go over here, h x1 plus k y1 is minus r square, h x1 plus k y1 minus r square, and divide by the under root of the square, sum of the squares of the coefficients. That is, in this case, is going to be equal to x1 square plus y1 square. This is Qn, and you're going to put a mod around it so that we get the positive value of Qn. Similarly, Pm is going to be the length of the perpendicular drawn from the point P onto this line. So x1 comma y1 is going to be put into this equation now, and it's going to become x1 square plus y1 square minus r square divided by under root of x1 square plus y1 square modulus. I hope you're understanding. AQ is the length of the tangent drawn from Q to the circle. AP was the length of the tangent drawn from P to the circle. Qn is the length of the perpendicular drawn from the point Q onto the chord of contact, and Pm is the length of the perpendicular drawn from the point P onto this chord of contact, which is given by this. Now I've got these values. I'm going to put all these values into this ratio relation that I had got, and let's see what we get next. Alright. So in order to be able to see what we get next, I'm going to erase this, and I'm going to write, therefore, I'm going to use these four. I'm going to use these four and put them in this ratio relation. I'll get under root h square plus k square minus r square divided by under root x1 square plus y1 square minus r square equals this divided by this. That will be equal to mod of h x1 plus k y1 minus r square upon x1 square plus y1 square minus r square. Okay. Next, let me square this relation that I have so that I get rid of the under roots and the modular sign. You can see the denominator here and the denominator here are quite related to each other. It's just that the square of this is equal to this. So I'll get one of the expressions cut. In the next part, I'm going to get h square plus k square minus r square times x1 square plus y1 square minus r square equal to h x1 plus k y1 minus r square whole square. That is all. This equation is the joint equation of the pair of tangents drawn from the point P, x and y1 outside the circle. So if you can see, h square, k square and this h and k over here will get transformed into x and y because I was finding the equation of the locus of that point. So when you solve the locus, eventually you convert h and k into x and y. So it's going to become x square plus y square minus r square into x1 square plus y1 square minus r square equal to x x1 plus y y1 minus r square whole square. This would eventually give me s1 equals t square. This is the equation of the joint, this is the joint equation of the pair of tangents drawn from a point P outside the circle. S1 equal to t square. What is S? S is the equation of the circle. X square plus y square is equal to r square. S1 is when we put the x1 comma y1 into the circle, I'll get x1 square plus y1 square minus r square is equal to t square. What is t? T would be the equation of the tangent had x1 comma y1 been on the circle. So that is x x1 plus y y1 minus r square. So S1 is equal to t square is the joint equation of a pair of tangents drawn from a point P lying outside the circle.